Number 9, which of the following substances does not form when a few drops of concentrated sulfuric acid reacts with potassium bromide? So there are two key reactions happening here. First of all is an acid-base reaction. So sulfuric acid reacts with potassium bromide, and H2SO4 will be acting as an acid, right? It will be a proton donor. It donates a proton to the bromine. So this is an acid-base reaction. So these are the two products that we get. The second reaction is a redox reaction, where the HBr can further react and we will get these products. Right. This is the redox reaction. Your sulfur has gone from +6 reduced to +4, and your bromide was oxidized to bromine. So which of the following does not form? We get bromine. We do not have hydrogen sulfide. Right, so B is our answer. Right, C will be here, and then D, sulfur dioxide, will be here. So the only thing we don't get is a hydrogen sulfide. Number 10, we have sulfuric acid. This amount neutralized by sodium hydroxide. This amount. What is the concentration of the salt form? So let's write out an equation first. Sulfuric acid, sodium hydroxide, we get the sodium sulfate salt and water. So this is our equation. Here we have concentration multiplied by volume, right? And remember to change this to dm cube. This will be 0.01 moles. For here, concentration multiplied by volume for sodium hydroxide, we ended up with 0.02 moles. So it tallies. We need twice the amount of sodium hydroxide for every sulfuric acid, right? So let's use sulfuric acid to find out the amount of salt. Ratio between sulfuric acid and the salt is 1:1. So 0.01 moles of sulfuric acid will give us 0.01 moles of sodium sulfate. We are expected to find the concentration. So the total volume of the solution is found here, right? We have added 10 cubic centimeter to 20 cubic centimeter. So the total volume of the solution is actually 30 cubic centimeter, which is actually 0.03 cubic decimeter. So this is the moles of salt. This is the volume that is dissolved in. So concentration is equals to moles over volume, right? And then input in our calculator, we have A. This is our concentration. Then part B, we are measuring the volumes by burette. So each reading having an uncertainty of plus minus 0.05. So what's the percentage uncertainty if you have to measure 10 cubic centimeter, right? So what we have to realize is we are measuring twice, right? For example, we start off the burette. Let's pretend that we have a reading A, and then we have a reading B, and in between the difference is 10 cubic centimeter, but we measure twice. So the first one has an uncertainty of 0.05, the first reading. The second reading has an uncertainty of 0.05. Right, taking the difference, we will get the volume. But to find the uncertainty, we have to actually add up the uncertainty for the two times. So the overall uncertainty to get the final reading is 0.05 plus 0.05. The uncertainty was plus minus 0.1. So this is our overall uncertainty. It was used to measure 10 cubic centimeter, so the percentage uncertainty will be 0.1 over the volume that we measured multiplied by 100%. Right, so that will give us a 1% uncertainty. Number 11. In water, hexanol, 6-carbon alcohol is less soluble than ethanol, the 2-carbon alcohol. So what is the best explanation for this? A. Hexanol cannot form hydrogen bonds with water molecules, but ethanol can. Now this is not true, right? Because hexanol also has the hydroxyl group that allows it to form the hydrogen bonds with water molecules. So it can form hydrogen bonds with water molecules. So A is not correct. B, carbon-carbon bonds are stronger in hexanol. This is talking about inter or intramolecular bonds. That is not related to boiling points or solubility. We are not breaking the bonds, the intramolecular bonds, when we are forming when we are dissolving in solvent. So this is irrelevant in the discussion. C, the forces between hexanol molecules are stronger than between ethanol molecule. Right, C is the answer. Right, we have a longer string, 6-carbon hexanol, right, compared to 2-carbon ethanol. So the London forces among the larger molecule is actually stronger. So this doesn't allow the water molecules to come into the spaces as easily as compared to in between ethanol. So the water molecule can surround the ethanol molecule more easily. That's why ethanol is more soluble in water. Number 12, as we go down the group, the halides, the hydrogen halides boiling temperature will change. Now I've pulled up a diagram to show you the changes in the boiling point. What we should notice is that the boiling point for hydrogen fluoride is the highest, right? And then it drops when it goes to hydrogen chloride, and then after that it starts to increase. So the trend is decrease then increase, but then of course we have to know why is that so. So first of all, why does hydrogen fluoride have this anomaly? Alright, so let's use the first three as examples. Hydrogen fluoride, although it's a very small molecule, it has very low van der Waals forces due to the small electron cloud, but it has hydrogen bonding. Unlike the other in the group. So because of the hydrogen bonding, it allows it to have a very high boiling point, right? Strong intermolecular attraction forces. So that's why it's the highest. Now, for hydrogen chloride and hydrogen bromide, okay, why is hydrogen bromide why does it have a higher boiling point than hydrogen chloride? Because it has a large, this is where the large electron cloud starts to play a part, right? Bromide is a much larger atom than chlorine, and because of the large number of electrons, the van der Waals forces is actually pretty appreciable. So its van der Waals forces is very high compared to HCl. So although HCl is more polar than HBr, right, but the fact that the large electron clouds of HBr will more than compensate and then allow hydrogen bromide to be a larger boiling point than hydrogen chloride. Right. The same reasoning is also for hydrogen iodide. Iodine is a much larger atom, so the van der Waals forces for hydrogen iodide is much larger. So from hydrogen bromide to hydrogen iodide, the boiling point continue to increase due to increase in van der Waals forces.